Hi, so in the previous module, we started looking at the multi-arm bandit problems, and we'll continue looking at some of the solution approaches for multi-arm bandits. So as you recall, in this case, we have n possible outcomes, right? And you have to select one of the actions from this set of n actions, and each action results in a reward derived from the probability distribution associated with the action. Right? And our goal is to find the most profitable action. Right? So the goal could have different shades to it, right? So we are interested in finding the best arm, but when or how are we interested in finding the best arm? So the simplest notion of solving the bandit problem is to identify the correct arm eventually, right? Regardless of how many ever attempts we take, as long as you can give me a guarantee that eventually I will be playing the best arm, that is sufficient. But then if you want to get more practical algorithms, we have to look at other notions of solving the problem. Okay, so you look at two here. So the first one is we would like to maximize the total rewards that you obtain, not just the rewards that you obtain eventually, but also the rewards that you obtain during the course of learning. So this is called sometimes minimizing the loss or regret while learning. So the regret is how much better you could have done if you had known the true solution from the beginning, right? So that quantity is known as the regret, and you would like to minimize the regret. And the second solution concept that people look at is called probably approximately correct solutions. So I'm interested in finding an epsilon optimal arm. The epsilon optimal arm is such that the mean of the selected arm mu is within epsilon of mu star, which is the expected reward for the best arm. Okay, I'm going to find an epsilon optimal arm that gives me the approximately correct part, and then I'm going to say that my algorithm will surely return the epsilon optimal arm, right, in 1 minus delta fraction of the problem instances. So with probability 1 minus delta, my algorithm will give you an epsilon optimal arm. So for fixed values of epsilon and delta, we try to figure out how many samples do I need before I can give such a guarantee. So the probably approximately correct framework, the probably comes from the fact that I'm interested in returning solutions with probability 1 minus delta, and approximately correct because I'm interested in returning solutions within epsilon of the true solution. So one of the most simple traditional approach is to essentially pull the arms multiple times, keep track of the reward that you get over time. So I would estimate mu hat I as the sum of the rewards I get when I pulled the arm I divided by the total number of times I have pulled arm I. That gives me an estimate for the average reward I expect to get when I pull arm I. And we know that this is an unbiased estimator of the reward, and hence with enough samples as time goes to infinity, these will converge to the true expectations, and I can derive the best arm by just looking at the arm with the maximum expectation, right? To ensure that we select the arms infinitely often, we use an epsilon-greedy strategy. So you select the arm that you currently think is the best arm, the arm star that gives you the max over all mu hat I. You select that arm with a probability of 1 minus epsilon, and epsilon is some small constant like 0.1 or something. And you can select any arbitrary arm with a probability epsilon. So this guarantees that that every arm will get selected, and therefore as the number of plays goes to infinity, then every arm gets selected infinitely often, and therefore asymptotic convergence is guaranteed for these kinds of epsilon greedy action selection. So one of the state-of-the-art algorithms that we will look at is called median elimination algorithm, right? So this is a pack algorithm, so it gives you probably approximately correct guarantees, and it tries to control the sample complexity. It's got one of the best known sample complexity for uh, solving a multi-arm bandit problem, right? So let's to get an intuition into how these things work. Let's start by looking at a simple algorithm which I'll call the naive algorithm. So you start off by sampling each arm L number of times, where L is given by the expression here. So it's 4 by epsilon squared ln 2n by delta. So n is the number of arms and epsilon and delta are the constants from your pack results, right? So you sample an arm, each arm actually L number of times, and let P hat be the average reward of arm A. So the output is essentially the arm that has the maximum of all the arms in the expected reward sense, right? So this obviously has a sample complexity of n by epsilon squared and ln n by delta. The real difficulty is to show that it actually achieves the desired performance guarantee. That is, that it will, with a very high probability of 1 minus delta, it will return an epsilon optimal arm. It will fail only with a probability delta. So we're not going to get into the mechanics of the proofs. It's quite beyond the scope of this course, but just I'm pointing out that you can come up with simple algorithms, and you can often show that they achieve the guarantees that you want. Right. So one of the drawbacks of the naive algorithm is the complexity depends on log n by delta. So you cannot avoid the order n term because you have to pull each arm at least once. But you want the additional factors to be dependent only on the epsilon and delta. You don't want to have an additional dependence on n in your algorithm. So Evandar et al. Devised an action elimination procedure which allows you to be pretty efficient in your finding the optimal arm. And it also serves as the basis for many other algorithms, and therefore I'll spend a couple of minutes looking at the median elimination algorithm. Right? The key idea here is that after some number of samples, you're going to eliminate some arms, and then you're going to continue sampling with the rest of the arms. Right? So here is the algorithm. It looks a little complex, but it's nothing really. It's fairly straightforward. Right? So you start off by having a set of all the arms available to you. Start off with an epsilon and a delta, and you start off with L equal to 1. That means that you are sampling L equal to 1, which is essentially the first round. So here now you sample every arm that is left, right? So in the first stage it will be all the arm set this many number of times, 1 by epsilon L by 2 squared log 3 by delta L, and let P hat AL denote its empirical value. So now what you have done, you have taken the arms, you have pulled each of them some number of times, and from that you have formed an estimate of the average reward of the arm. Now what you do is you arrange these averages in some sorted order. So let's say you arrange the averages in ascending order, right? And then you take the first half, the half that is below the median, right? So the half of the data that is below the median, you take those and you eliminate them, right? And now what you are left with is half the arms which had the highest possible expected mean from the previous round. Okay. So now you repeat the whole thing again, except that you make your epsilon and your delta even smaller. So with a little bit of algebra, you can actually show that this gives you nice performance guarantees. It gives you a pack result, so it gives you the epsilon delta guarantees. In addition to that, you can also show that it has a sample complexity of n by epsilon square log 1 by delta. We go off n by epsilon square log 1 by delta. So we've gotten rid of the n in the logarithm. That's a big step, and it turns out that it's very hard to improve on median elimination algorithm, at least using these kinds of processes that we were looking at. But in practice, these kinds of pack guarantees are weak, right? And typically, you can get acceptable performance with far fewer samples. And the pack algorithms also do not care about how your performance varies while you are learning, and hence, increasingly, regret analysis of data is becoming more and more popular. Right? So here is a very simple algorithm that can be shown to give very good regret performance, right? So you not only maintain the best estimates, or the estimates of the rewards that you have so far, but you also maintain some kind of an uncertainty interval around the reward, right? So look at this orange curve here. So this is the mean reward that I have, but then I also have an uncertainty or some kind of a confidence interval here that says that, hey, my true reward with a very high confidence would be within this interval. So you can see that for some arms, even though the estimated mean rewards are lower, the uncertainty is much higher. And so what we really are looking for is, so if you have the best estimate R, and the other arms are played only if the upper bound of a suitable confidence interval is at least R, right? But one of the simplest approaches could be just be greedy with respect to the upper confidence bounds. You estimate the upper confidence bounds, and then you take actions that have the highest upper confidence bound. That's obviously going to be something higher than R star, and essentially in this case you would play the arm red as opposed to orange and blue, even though orange has the higher expected mean, right? So you can show that the suboptimal arms are played fewer than 8 by delta j times, where delta j is the difference between the optimal arm and the suboptimal arm, right? And this allows us to come up with very efficient bounds for this upper confidence bound algorithm. It's called UCB, right? So the algorithm is very simple. So at any time you play the arm j that maximizes xj bar, which is your average reward so far, plus this funny expression under the root 2 ln n by nj, where n is the number of arms and nj is the number of times you have played arm j so far. So that expression actually comes from estimating upper confidence bounds, and this helps us show that the suboptimal arm can be played, will be played fewer than 8 by delta j ln n times. So what are the implication of all of this? I'm giving you a lot of numbers, but in practice you don't really have to worry about these numbers, because all you're interested in is figuring out with the fewest number of samples can I estimate what the outcome will be, right? And UCB essentially gets you there very quickly, even though it doesn't guarantee that it gives you the best outcome, but it reaches there and it reaches close to the best outcome pretty quickly, right? So I was talking about showing ads as one of the use cases, but if you think about it, for each user you'd like to show different ads. You don't want to show the same ad to different users, right? But if you're using a single bandit algorithm that is learning the preferences of all the users, that's what you'll end up doing, right? So one solution around this is to build one bandit for each user, right? But given the large volumes of users that are likely to come to your page, and the restrictions on computation and such, that is not feasible. So what we do is you typically share features across different users, right? So it could be demographic features, it could be browsing history, it could be location, or if we're talking about patient data, it could be history and the patient history. So it could be a variety of different features that you would share, and your expected reward for getting the for pulling the arm will now be represented as a function as opposed to being a number. It's a function of these features, right, as opposed to being a single estimated number, right? And so you can solve this in many different ways. You can assume that each user is represented by a set of features, right? It could be set of joint features of the user and of the arm, right? and the statistics used for choosing arm is now dependent on this feature. This is essentially what I was telling you. The statistic in some cases can just be the mean reward. It could be the upper confidence bond and variety of things, right? So the simplest case is to consider that for each feature combination you have a different bandit. And once a choice is made, that's a stochastic transition to another bandit. Just to make it conceptually easier, right? But that's not really the case, because each of these bandits are going to be closely interacting, right? Because the feature values might be similar, in which case the outcomes for one bandit could be the same for other bandits, right? So earlier work there was on associative bandits, right, where typically use a small number of states to encode these features, and you don't really worry about functional representations for the values, right? So once I have a function that is going to output a value, a real value as a function of features, what would you think of doing? Exactly. So we could do linear regression, right? So where UCB variation, where you use linear regression to predict the mean rewards, and you use a upper confidence bond derived from the linear regression algorithm. It's called LinUCB, and it's one of the more popular contextual bandit algorithms out there, right? So the expected reward is assumed to be a linear function of the features. People typically end up using rich regression, which is L2 penalized linear regression, to fit the parameters, and you can derive upper confidence bond for the regression fit, right? So it gives better performance with lesser training data, right? So this here is a simple set of results for predicting click-through rates on ads, and you can see that if only 1% of the ad data is available for training, available for estimating the parameters, you could see that LinUCB methods, which are this and this, do much better, right, than regular UCB methods, which don't do this generalization across different users. So you can see that 5% data again. So the LinUCB variants are doing better, but then if you have a lot of data available for training, you could see that the other methods pretty much catch up with LinUCB. So the idea here is that with LinUCB you have better performance with lesser training data, right? And so people now are looking at more powerful approximations, looking at Gaussian processes, looking at other more complex sampling techniques. A lot of work going on. It's a very active area. So people are looking at budgeted bandits, people are looking at case where there are adversarial bandits, and then people are looking at dependencies between samples and multi-slot cases, and many different problems that people are studying in the bandit literature, right? One thing of interest is to consider what I call a full reinforcement learning problem in the contextual bandit case. So you have a context, the user comes and picks an action, and after that you just move on to another user, right? But in the full reinforcement learning problem, so you have to make a sequence of decisions before you can truly solve the problem. So you're faced with a situation or a state or a set of features, you take an action, and then that results in the set of features being changed, and then you have to take another action and another action and another action until the problem is solved. So think of the question of riding a cycle, right? All of you know how to ride cycles, but think of how you learn to ride a cycle, right? So you didn't learn it through supervised learning. There is nobody telling you how to turn what pressure to put on a pedal, and what angle you should tilt your upper body and things like that. If people had been telling you the technical aspects of cycling, you probably wouldn't have learned to cycle. All you do is get on the cycle and make sure you don't fall off, or if you fall off and you get hurt, you don't do the thing again the next time, and soon you find yourself cycling, right? So this is essentially a form of reinforcement learning, where each action you take, I mean, if you make a bad move, you're just going to keep tilting until you fall, right? So each action you take causes a change in the state, and you have to compensate for that and then continue learning, right? So this is called the full reinforcement learning problem, and the ideas that we describe here, like pack MDP and optimal exploration and so on and so forth, have been extended to the reinforcement learning problem as well, right? So here are a couple of few tutorials and source material for learning more about bandits if you're interested. So that brings us to the end of the module. Thank you.